recording. You mean it was a surprise how it actually gives you the number of bytes in the array, or? So I gotta say, pointers are the hard thing about C. And there are a couple other things that are peripherally related to pointers because they kind of are pointers, and those things are strings and arrays. And because of that, because of pointers being challenging, because of strings and arrays being related to pointers, suddenly all that stuff becomes challenging. So pointer arithmetic is definitely interesting. Yeah, that size of thing. So if you do the size of any object, they call them in C parlance, even though object, it's not object in the sense that you're used to in object-oriented programming. Take the size of any entity, we'll call it like an array. It's going to return the number of bytes that that thing takes up in memory. So let me get some scratch paper here. Scratch paper. So if we've got something like this, maybe this guy takes up 4 bytes, and it really depends on the architecture, how many bytes this takes. So I'm saying on this particular demo architecture, let's say it takes 4 bytes. And if we have an int array, this thing's gonna be 12 bytes. Because if one int is 4 bytes, then 3 ints must be 12 bytes. And so if we want to figure out the number of elements, VI fail. If we want to figure out the number of elements in the array, we got to take the size of B, which is 12, divided by the size of A, which is 4. And this gives us 3, which is the number of elements in the array, right? Of course, you could do, we did size of A because that was an int, but you could also do size of B sub 0, just like you were saying, because that's also an int. And technically, because these are variables in here, they're not types, you actually don't need the parentheses here. So you might see size of used like this without parentheses from time to time. It's really common for people to put parentheses around it, but it's only actually required if you put a type in there, like int. Yeah, so what we're seeing right here, this thing you brought up, Thomas, we're seeing like kind of a window into how low level C actually is. That it has a size of operator that returns the number of bytes that a thing uses in memory. And we don't actually have an array length operator anywhere, which is kind of funny, right? Because if you think about what you have in a higher level language, every array that it maintains has a length associated with it, right? But in C, arrays don't have a length associated with it. It does at compile time when we said, oh yeah, B is an array of 3 ints, right? Oh, that's weird. When I use the VI cursor move keys with my left hand, I use them backwards. That's very strange. Today I learned I can only use VI cursor keys with my right hand. So we declare that it has 3 elements in it for sure. But all that does is that the C compiler is like, okay, I'm going to allocate 12 bytes right there for that. That's it. You got 12 bytes. It doesn't actually maintain any knowledge of the length of the thing. Like if we were to write some code like this, we want to print out the value in B99. What do you guys think is going to happen? Actually, the compiler might warn on this. The compiler might be smart enough to warn on that one. Yeah, it's probably going to print whatever's in memory there. It's going to go have a look. We have got a chunk of memory of 12 bytes set aside for B, but we're asking to get stuff way out there, way past the end of it. If I want to make sure the compiler is not going to warn me, I might have to do something like this. But same thing. We call this in C, we call this undefined behavior. And it could print out some random stuff of whatever's there. Or it could crash. It could do almost anything. In C, when you get into undefined behavior land, all bets are off. The program could do anything at that point, according to the spec. This is absolutely a buffer overflow, or maybe a buffer overrun, it might be called. We've got a buffer. A buffer is just another fancy name for a chunk of memory. And if you access stuff outside that chunk of memory, then you are overrunning or overflowing the buffer. And so we have a chunk of memory here, 12 bytes allocated for B, the array, and we are accessing memory way outside it. So yes, it's now in another language like JavaScript, if we tried to do something similar to this, actually JavaScript's perfectly happy doing that, right? It'll just print out undefined or something, won't it? Is that what JavaScript prints out if you access outside? I can't remember. In any case, JavaScript doesn't crash when you go outside the bounds of an array. Now a quick peek. Nodes. So A is an empty array, and A99 is undefined, right? All right. So each address here, Vim, I'm not going to use the word address here yet, because I think that has special meaning. But maybe I want to make sure I understand your question. I would say that here in this example, each slot that we have for elements in the B array, those are all 4 bytes. So B0, 1, 2, 1 and 2, these are all 4 bytes each. Is that the question you had? Is each memory location 4 bytes? That's still a weird question for me to answer. No, I'm going to go with that. Each memory location is 1 byte. And we talk more about this when we get to computer architecture. So if each memory location is 1 byte, then a variable such as A, which is 4 bytes long, must take 4 memory locations. And this whole array takes 12 memory locations. Technically, it's possible to have computers that have memory locations that are different sizes than a byte, or rather, I should say different sizes than 8 bits. But in this modern day, all computers you're going to run across, all their memory locations are 8 bits long, commonly known as 1 byte. And then numbers that are larger than that just take up multiple memory addresses. We do all ints take up 4 bytes? The answer is no, because on some platforms, ints are 2 bytes. On some platforms, they're 4 bytes. On some platforms, they're 8 bytes. So it varies. What we do know for sure is that one int takes size of int bytes. So we shouldn't hard code the number 4 anywhere. If you want to know how many bytes it is, use the size of operator and do all your math based off of that. Let's bring this up really fast. Oops, getting ahead of myself. Let's just have a peek. Unsigned long. I got the wrong format specifier. Size of returns a type called size underscore t, size t, and I keep forgetting if it's a this or if it's a unsigned long. All right, woohoo! Ints are 4 bytes on this computer. Let's check out some other sizes. So if we have int, we have our int b array that we had before. We should be able to print that out and see that this should be 12. So here we should get 4 for int. I'm guessing long is probably 8. It's a long integer type. And b, we know that size of int is 4, so 3 of them should be 12. So I'm guessing 4, 8, 12. If you were to bring up your old MS-DOS emulator and run this program there, you would see different numbers. You would see 2 for size of int, and you would see 4 for size of long. I'm a little bit surprised ints are only 4 bytes, actually. So the size of is in bytes, yes. So anytime you use the size of operator like this, it always returns the size in bytes. Let's see here. Where should we go from here? We can do some asterisky stuff. Asterisky stuff. Asterisky. Let's see. Fizzbuzz strings. We get into asterisks with strings right away, right? Let's talk about pointers a little bit. We can segue this into pointers. All right, before I go into pointers, was there anything else that was not pointer related, not string related, and not array related? Anything else besides those topics that we can address first? Any other questions? So anything except pointers. I hate it when I do that. I accidentally double click this thing, it gets big. Anything besides pointers, strings, and arrays we could talk about? Did all the rest of it make sense? How do we feel about things like needing to declare the types of our variables and stuff? Oh yeah, that's an interesting one too, because you're used to all this kind of, we call it like namespacing, right? If you have a module in Python, you say math dot, and the same thing in JavaScript, you've got the built-in math library, math dot square root. Yeah, C is too low level to have that concept. So it definitely has what we call scoping, the stuff that you're used to with like B being local to this function right here. So B is local to main, and if you had another function here and you had another variable here, this b here is local to function foo. So that kind of scoping happens. And we also have file scoping. So normally foo, the function is only visible within this file right here. And if you had a different C file and you tried to compile them together, that other C file wouldn't normally be able to see foo unless you explicitly declare it, usually in a header file. But that's pretty much as far as it goes, and it doesn't do anything like math dot or something like that. And what this means is that there can only be one square root function, sqrt. That function can only exist in one place ever. And even if I tried to make my own local one here that does something, then if we tried to compile this and link the math library to it, the compiler would be like, I don't know, if you have two square root functions, I don't know what to do. So you simply can't make functions called that. It doesn't because that issue happens at a different time. It happens when the program is linked together, we call it. So at compile time, you'll be fine when it does the compile part of it, where it's going through the C code and turning it into machine code. But then when you try to link the whole thing together, it'll complain that there are duplicate square roots. The same thing more commonly happens with main, when you accidentally have two mains somewhere, like maybe you copied and pasted some code that you were going to use and it had a main in it, and you try to link. And I actually should clarify that. This might not happen unless we've declared this to be an external function, but I'm not sure. Do other functions have scope, or only that, or only one of that name ever? So actually, let me do a test. Make sure I'm not lying to you about this. Let's do a test really fast. So I'm going to have a function foo here, and actually let's make this add 2. I'll just call it add. I don't think we have an add. Okay, and this is going to return a plus 2. So there's one function, and I'm going to make another one right here. This one's going to return a plus 4, just so we know it's different. And then we're going to make a call to it. All right, and then I'll try to compile this thing and see what happens. Nope, it puked. So it was in a different file. So when it compiled up, I could elaborate a little bit more on these two phases. The compile phase takes your source code and turns it into machine code, and it actually turns it into this intermediate code called object code. And you end up with these object files. And if you take those object files, then you go to the next phase of compilation called the link phase. You link those object files together into an executable file. And the executable file is what you actually end up running. Usually these two phases are crammed together and we don't notice them. So right now when I said compile this, it went through the compile phase, no problem. It got to the link phase and it says, hey, I got this duplicate symbol. LD is a historic name for the linker. It stands for load, but LD on Unix systems is like, I'm trying to put these object files together to build an executable, and I've got two versions of add in here, and I don't know what to do with that. I can break that compilation process up into steps here. We can do GCC -C. You don't normally have to do this, so we're kind of off in the weeds a little. But if I do gcc minus c foo.c, that'll do a compile. And now I have an object file called foo.o that just got created. And I can do the same thing for bar.c, the other one that has my add in it. And now I've got both foo.o and bar.o. These are the object files. So the compiler has successfully built my source code. It's like, oh, hey, you've got a main and an add. I'll build that into an object file. And you got this other file that has an add in it. I'll build that into an object file. No problem. But now we want to link them together. And so I'll pass both object files to GCC and tell it to build an executable for me. And this is where the linker comes into play. And it says, oh, hey, I looked in these object files right here, and you've got a duplicate symbol, so blah. Oh, the significance of underscore. So I'm going to give you two answers to that. This is a great question. From a compiler standpoint, it does not care. Underscore, just another letter. But from a human, what's the word? The word is just gone. Convention standpoint, underscore implies that this is a private function that you're not supposed to use. It can also imply sometimes that this is an extremely low-level function, like part of the operating system or something. But anytime a C programmer sees an underscore in front of a function name, it sets up flags in their head saying, maybe I shouldn't be using this function. Maybe they didn't want me to use it. It's something that has to be exposed for some reason for the rest of the system to work, but people that are just interfacing with the system probably aren't supposed to touch it. Oh, but I see. You're asking why is it underscore in front of this one right here? I know the answer to this in my brain somewhere. Stumped me. Let's have a look. I know the answer to this for some reason. Why does it do this? The ABI required, the application binary interface required underscore, but why? But why? I don't know. I might have to dig into this later. I swear it's a fact in the back of my brain, but I'll have to dig that up. I'm curious now. Anyway, let's save that for another time. Let's see. Let's do some asterisk stuff. How about that? I think I can come back to my example here. Let me bring up this guy. Thanks, JJ. What is the answer? It's easier to mangle the names than go backwards and fix all the existing code. All right, so COF and ELF object files. ELF I know is one that Linux uses. I don't know what format object file we're getting here on the Mac, but apparently it still likes underscores. This is a good term to know, name mangling. This is the concept that your compiler takes something that you've written, like add, and then does something to it to change the name somehow. Like put an underscore in front of it, or if you're in C++, put all kinds of crazy stuff in front of it. So there were a bunch of old assembly language libraries, and there were name collisions. So in these assembly language libraries, people had named things like add, and if you wanted to use that, then you would have had to call it something else in your C program, which would be really annoying. So they decided that they would just put an underscore in front of every single thing in your C program. And that way, when the linker got to it, it would see that you had underscore add versus the assembly library that had just regular add in it. And so they would be different things. What a hack. This is the other thing I was talking about outside of assembly. Yeah, awesome. Good to know. We're gonna blow all this away. All right, let's do some pointer things. What should we start with? Probably strings. Maybe strings. Seems like a good way to start. So in the video, I assume that there was something like this someplace. I'm trying to remember. Does this ring a bell, or have I started too far? Uh, yeah, for main. So this is what I'm about to tell you applies for the main function only. The main function is a special case in the spec. So normally, if you have any function that says it returns something, like here I've got a function foo that says it's returning an int, you absolutely must return an int. You have to. And if you don't return an int, you're going to get a compiler error right here. That said, main is a special case. Historically, it returns an int. This is a value that comes back to the operating system so that you can test to see if your program succeeded or not. And 0 means success in this case. If the compiler gets to the end of main and there's no return, it will assume you meant return 0. That's a special case for main only. Some compilers warn if you don't return 0 at the end of main. So I like to explicitly return it because we're saying right here that main returns an int, so I feel it's more correct to explicitly say. Yeah, why on earth isn't it 1? Why doesn't 1 mean success? Because 1 means true, right? That's totally a valid way of thinking about it. And I believe, although I've never seen this written down anywhere, I believe the rationale is this. There is basically one way for a program to succeed, but there are multiple ways for it to fail. So 0, in a way, makes sense because 0 means, because that's the single way to succeed, right? The program, everything went right, we return 0. But if something goes wrong, we can return non-zero. Hey, that went wrong. But if a different thing goes wrong, we can return another number. Or if a different thing goes wrong, we can return yet another number. And so by examining the return value of the program after the program exits. If it's 0, you can say like, okay, nothing has gone wrong. If it's non-zero, something's gone wrong. And you could examine exactly the number to get more information about what went wrong. If we do a quick run of this thing, where's my... nothing happens. But here at the shell, you can actually look at the return value for main. It's in the variable question mark. And in bash, you put a $sign in front of all the variable names you want to see. So if we look at $sign question mark, we'll see that the last program that ran exited with a status of 3, which is indeed what we returned right here. So if you're writing bash scripts, you could have a bash script run your program, then test the return value to see if it succeeded or not. If I change this to return 0, rerun the compiler, rerun the program, and check out the return value, you see now that it's 0. So that's where that number comes back out again. I'm going to simplify this example with the pointers. Let's start even simpler. I'm going to make a char C. So char is a type that holds a single character. But really what it is just a very small number. If I ask how many bytes the char is, anybody have a guess what that's going to turn out to be? What the size of a char is? One byte. In fact, the spec goes so far as to say size of char is always 1. So we've got 1 byte of memory, and in a byte, it's 8 bits. It's like an 8-bit number, and we haven't really talked about what that means yet, but what it means is that if it's an unsigned number, it can store values between 0 and 255. So it's like a very small integer. Usually we use them to store single characters in, but you could also just put a number in there if you wanted, because single characters are actually numbers. Have you guys seen the ASCII stuff yet? Like each character corresponds to a particular number. Let me print these out for you guys. Let me change that to the letter C for more fun. All right, what's this one going to print? Not a trick question. Just waking everybody up with this one. 66. We're saying, hey, print out a number. Print out whatever's in C. What's this one going to print? Does anybody know? You said D is the letter C. 67. How did you know that? '65 is capital A. 66 must be capital B. 67. If you want to know what values correspond to which characters, you want to look up the ASCII table. Apparently at ASCIItable.com. I don't know why that makes me laugh. Some dude's like, I'm going to make ASCIItable.com, and it's going to get tons of traffic. I'm not going to put ads on it. He's winning. So yeah, looking down in this table, it's kind of small. I see we got decimal, hexadecimal, and octal. And so the decimal column, we've got B is 66, C is 67. So all these numbers correspond to different letters. We got uppercase, we got lowercase, we got punctuation, we got numbers, and then we have all these control codes. These are called unprintable characters. You can't see any of them, but they have special meaning. So anyway, the ASCII table's got all that information in it, and we're just printing these things out. But what if I say, let's print out, yeah, that's right. Let's print out D as a character instead of as a number. We'll print out C as a character instead of as a number. D is already, we know that's C. But if we want to print out the variable C as a character, that's going to print B, because 66 is a capital B, as we saw in the ASCII table. So I'm thinking if we run this, we're going to see 66, 67, then B and C. I swear this is getting to pointers. And then we've got these two chars that hold these two different numbers. So one of the takeaways here is that if we decide to interpret these variables as numbers, then we get numbers as output. If we decide to interpret them as characters, then we get characters as output. And that's printf behaving differently in both cases. Whoa, that took a while. So there's our B and C as numbers and the B and C as characters. Any questions about that before we tear off into pointers a little more? I want to make sure that all makes total sense. I can elaborate that we know the size of char is 1, so we know that 1 byte of memory is set aside for C, 1 byte of memory is set aside for D. And stored in those memory locations, we have the value 66 in one of the memory locations and the value 67 in the other memory location. How's everybody feel? Now that I've said memory location, we're getting into pointer land. All right, I'm going to blast on here. I have a mental model for you guys of how to think about computer memory. I want you to think of it like a big array of bytes, where each byte is a number that can store a value between 0 and 255. So imagine memory as being this big array. Let me ask you this. If you want to get a value out of an array, what information do you need to have to get a value out of an array? You gotta have an index. That's right. Without the index, you can't put stuff in the array or get stuff out of the array. And so if you talk about a piece of data in an array, you're kind of talking about two pieces of data. One, you've got the index, and two, you've got the value that's stored at that index. So they're kind of two things. I might say, give me the value at index 5, and the value at index 5 might be 99. So two values, 5, 99, they're related. I don't know why I held up 2 fingers for 99. That was, maybe I just had no other options. All right, so keep that in mind. Now, I'm going to give you another name for the index. Remember, we have in our big memory array, we've got an index. I'm going to give you a different name for that. Instead of index, I want to call it a pointer. I'm gonna let that sink in for a second. A pointer is an index into the memory array. What's everybody think of that? Skeptical? Intrigued? I want to know if I mean, I know we don't have enough to work with yet, but I want to know if that feels like a demystifying step or more of a confusing step. Hold off on that second part. Let's do some tests here. So I've got a variable C, and it has the value 66 in it. And we know that we can print it out. I want to find out what memory address. Sorry, I've used a different word. I want to figure out what the pointer is to C. I want to figure out what the index in the memory is. So in our big memory array, I want to know what C's index is. Let's say. There's another term that I'm going to use here interchangeably with pointer, and that is address. So now we got three words that mean the same thing. Pointer, address, index into our memory array. These are all the same thing. So if I use them interchangeably, forgive me. So if I want to figure out the address of C, that is a pointer to C, that is C's index in the memory array, we have to use the address of operator to make that happen, and that's an ampersand. I'll use that in just a second. But an address is the same thing as a pointer. So I'm going to use this terminology kind of interchangeably. I'm going to make a char pointer P. So this is a variable that points to a char. That is, this variable contains the address of a char. That is, this variable contains the index into memory of a char. Remember, we had two different numbers we wanted to keep track of when we used arrays. We had the index and we had the value stored at that index. So here, P is going to be like our index, and C is going to be like the value stored at that index. Now, it's important to note that this is a declaration of a variable right here. We are making a new variable called P, and when you're making a new variable, the asterisk has a certain meaning in this context. The asterisk has a lot of different meanings in a lot of contexts. Sometimes it's part of a comment, sometimes it's a multiplication, sometimes it's a pointer dereference, sometimes it is a pointer declaration. So it's important to keep the context of the asterisk in mind. So right here, we are declaring a new variable P, and we're saying this is a pointer to a char. Right now, it doesn't point at anything. Just as if we declared an int X and we didn't assign it to anything, this just has some garbage in it. And this also has garbage in it. It's a pointer to whatever. We don't know yet. We haven't assigned it. Char pointer P because it's a memory location, right? Because it holds a memory location. But why char? So to rephrase your question, make sure I have it right. This is a good question. If this is an index into our memory array, and each memory element is 1 byte, isn't this also an index into our memory array, where each element is 1 byte? And if they're both indexes into the memory array, why does it matter if one is char and one is int? Is that your question? Yeah, that's a great question. And I'm going to hold off on answering it. The answer has to do with the compiler being able to do pointer arithmetic correctly. But let's get to that in a bit when we get to pointer arithmetic. For now, it's good enough to know that if you have a pointer to a char, you should be referring it to a variable that is also a char. So right now, p points to nothing because we haven't initialized it. We could just point it to some arbitrary memory location if we wanted. We could do that. We have no idea what's there. Probably not a valid memory address to access. So it's pretty rare that you see a pointer getting assigned an actual fixed value. It's usually like on embedded systems where one memory address corresponds to something specific in hardware or something. But in normal C programming, you really never see this. You could do it though. And it's no harm in setting this value to point there. The harm comes if you decide to look there or if you decide to store something there. So instead of just doing an arbitrary memory address, let's look specifically at the memory address of C. So what we need is a way to get the address of C. Remember, address is a pointer, so the address of C is exactly the same as a pointer to C. Did that get covered yet? Or if I ask the question, how do I get the address of C? I don't know if we got that far yet. Ranging ahead a little bit till tomorrow. So it turns out there's an operator, the ampersand. And this means address of. Remember, the address of is exactly the same as a pointer to. So this will tell us a number. This will give us the number in memory, the index in memory, where C is actually stored. And then it will set that index. It'll store that index into P. Let's print one of these out and see what happens. If the address pointer is the same, can we do dereference C? You can't because C isn't a pointer. C is merely a char. So C is neither an address nor a pointer. P is a pointer, and it contains an address. I had a finishing sentence for that train of thought. Where did it go? So P contains a number. Let's print it out. And there's a %P for printing out a pointer. It's just coincidental that %P and this P variable P are there. %P always prints out a pointer value. So let's print this thing out. This is a hexadecimal number. Let's figure out what it is in decimal. Oh, how do I get this out of scientific notation mode? I saw for a second, it actually showed the value. Is it too big to print out in Node? There we go. All right. Good old JavaScript to the rescue. So this right here is the address, this gigantic number, which is okay because I've got a lot of RAM in this computer. So this gigantic number right here is the index into memory that the variable C exists at. So if we want to store some data, like 66, we need a spot in memory to store that. And the compiler has decided, or the runtime has decided, I'm not actually sure who decides. This right here, address 140732702370587, is the address that we're going to store that number at. We could store another one here. Let me just print out the address of D. We can see if they're sequential. They might be sequential. They might not be sequential. I don't think there's any guarantee. They are. So here I've declared C and D. I've printed out pointers to both of them. That is their index in memory for both of them. And we see they are sequential, one's right after the other in memory. Doesn't have to be, but I think C compilers do that a lot. What's everybody think about the story so far? We've got our big memory array. We've got number 66 stored in it somewhere. We've used the address of C to figure out where it was stored, and we printed out that index. What's everybody thinking? We still haven't done some stuff, like we still haven't looked at that address, we still haven't changed values at that address. So that's where more asterisks come into play. But using hexadecimals to store addresses, I love this question. And it's something we talk about more when we get to computer architecture, but I can totally give a sneak preview for it now. But the gist is this: there exists a numeric value that is the address, and hexadecimal and decimal are just different ways of writing that same numeric value. So here in Node, when I said, hey, here's that hex value, Node printed it back out in decimal for me. These are the exact same value. They are just a different way of showing it. It's like a different language for writing the number out. This one happens to be a base 16 number, and this one is a base 10 number. We could also write it out as a base 2 number if we wanted. Let's just do that. There we go. So this value right there, base 16 number, this value, base 10 number, this value, base 2 number, these are all the exact same value, just a different way of writing them out. So it's not that the address is stored in hex. The address is just a numeric value. It's only when we print it out that we decide which base to print it in. And so printf, when you give it a %p modifier to print out a pointer, I'm not even sure it's in the spec, but every single implementation I've ever seen prints that number out in hexadecimal. So does that make sense? It's not that it's the address is hex. The address is just a number. It's just a numeric value. It's merely how we've printed it out there versus printing it out in decimal or printing it out in binary. The example I use later on is like if there are 12 apples on a table, everybody agrees of the number of apples on the table, regardless of whether or not we write it out as 1100 in binary. It still represents that 12 apples. We write it as 1, 2 in decimal, still represents 12 apples. We write it as 0C in hexadecimal, still represents 12 apples. Just a different way of writing it down. Likewise with the address here. And when you're programming, you should probably just consider things like 66 to be stored in a pure numeric sense. Not really that it's stored as base 10 or stored as base 2 or stored as base 16. You just think of it as 66, the pure mathematical value. Peaks and pokes. Yes, Thomas, this is absolutely true. Let me come back to that if we have time at the end of the hour. But it's definitely break time right now. All right, I'll put that on the list. All right, so the story so far, we've got a value stored in memory somewhere. We've figured out where that somewhere was by using the address of operator to figure out what the address of or the pointer to that value was. And then we printed that out so we could see what the memory address was. It's pretty rare to actually use %p and print stuff out in real life. Barely anybody does that because most time you don't actually care what the address is. But we've done it here just to demonstrate that the address is just a number that is just an index into memory. All right, let's take a break because it's been an hour, so we'll do a 5-minute break. And what? When we come back, we'll do some more asterisk stuff to look and see what values are in memory at addresses and also change those values. And then we should be able to tie this in to how strings work. And then we should be able to tie strings in to how arrays work. So here's the plan. All right, any questions before break? Everybody's ready to go get more coffee? I'm going to put a poll up about pointers, so go ahead and answer that, but I'll see you guys in 5. Everybody coffee up? Like mad dash around my house to get the hot water going. All right. So in the last 5 minutes, are there any, what can I say about what we've done so far? Or what can I address to clarify? If anything, or are people just waiting for more context? There's a lot of learning stuff in computers is just taking in facts and relying on later context to give them meaning. Should I just keep launching ahead? If we didn't do char pointer p and just did int p, would it work? It would not. If we did this, the compiler is going to complain on a type mismatch right here. It's going to say, hey, I've got an int on the left side and I've got a char pointer on the right side. And so the types on either side of the equals are different. And the C compiler is pretty good at converting numeric types, like converting a float to an int. It'll do that for you. But if you want to convert a pointer to a non-pointer, it will complain about it fairly vociferously. Blah, incompatible pointer to integer conversion, assigning to int from char pointer. So yeah. And even if we made this a pointer, we're going to probably have some problem. It's only a warning. It's not an error, but saying, hey, incompatible pointer type assignment. We've got a char pointer on the right side. We've got an int pointer on the left side, and it's being unhappy with it. All right. Well, let's keep doing some stuff here. So we know where in memory that value 66, otherwise known as C, is stored because we've got a pointer to it. The pointer is just the address, so we know the index into memory where it is. The question is, what can we do with that? Why would we bother? Why would we bother having a pointer to a thing when we could just say, we could just change C directly? Gives us more flexibility that will become apparent later, but this example is going to be kind of contrived. I'm going to print out a couple things here. I'm going to print out, we'll start with the value of C, which should be our good old 66, if I run the right thing in my command history. So all I did here was print out the value as a decimal number. So that printed out 66, as expected. But what if we wanted to get at that value through the pointer, via the pointer? So this is where the fun begins, right here. So we know that P contains the address of C. So P is the memory location that has that number 66 in it. Remember how we were saying earlier that memory is like a big array, and once you have the index into the array, then you could do stuff with the array, right? It's the exact same thing in pointer land. Once you have a pointer to a thing, that is, once you have the address of the thing, that is, once you have the index into memory of the thing, you can do stuff with that thing. So here we have pointer P, which has the address of C in it, which means we could do stuff to C with that address, with that pointer. One of the things we can do is print out what's in it. So here's another one of those asterisks. This is a different context than before. Like before, when we used the asterisk, we were in a variable declaration. We were making a new variable called P. And so the asterisk here means this variable is a pointer type, as opposed to this variable, which is not a pointer type. But here in this context, just out here in our program code where we're not declaring anything, asterisk has a different meaning. This is the dereference operator, we call it. And what this does is it said, oh, sorry, this is a typo. I've been totally confusing you guys. I'm so sorry for writing C there. Everybody's probably like, what are you doing, Beej? Makes no sense. Oh, so apologies, that should be P. So what this means is instead of P, the pointer, like earlier we used the %P format specifier to print out the value of P. This asterisk here means print out or give me the value of the thing that P is pointing at. Give me the value at that address. So what's this line going to print? $66. Let's think that through. We've got a char C, it's got the value 66. We know that 66 has to be in memory somewhere. All variables are stored in memory somewhere. Where exactly in memory? We can find out with the address of operator. So we take the address of C, we figure out where it's stored in memory, and we store that result in the variable P, which is a pointer to it. So now we have P pointing to C. And since P is the index into memory, we can do stuff at that index. And by dereferencing P, that's saying, hey, give me the thing at that index in memory. And so it goes and looks it up and it sees that it's 66. If we build that, it should work fine and print 66. So we've got three things printed here. We've got 66 printed directly from C. We've got the address of C, which is that big number. And then we've got this thing at that address, which is 66 again. So we've kind of come full circle. We got 66 in memory, we got the address of that thing, and then we looked at that, what was at that address. The dereference here is kind of like depointering the pointer. So P was a pointer to a thing, but if you put the dereference in front of it, now the expression is the thing. Not the pointer, but the thing that was being pointed at. Let's see, double checking. Asterisk need pointer when declaring a variable and dereference it anywhere else. Yes. Thomas, except I'm going to add one more asterisk there and say anywhere else unless it's a multiply or a comment. Can you say the asterisk cancels the ampersand? Yes, that is a great way of looking at it. Because what have we done here with this ampersand? We've gone from a variable to a pointer. And then with the asterisk down here, we've gone from the pointer back to the variable. So ampersand gets us a pointer to a thing, and asterisk gets us back to the thing. It's a great observation. Nobody ever writes this, but I think that might actually work. Get into what Vim is saying. Give us a pointer to C, and then go back from the pointer and get us back to the original thing. I'm actually curious if this is going to compile without warning. It totally does. And if we print it out, oops, compile. Yeah. So there, in one crazy line of code, is exactly what Vim's talking about. Use the ampersand to get a pointer to C, use the dereference to get back to C, and then I assign the result into D. And then when we printed it out, sure enough, it was 66. Of course, nobody ever writes this because why would you turn it into a pointer and back? But cool. So we've successfully gotten what the thing is pointing at. We can also change what's at the address that P points to. Let's do this. So this line of code, this says, hey, the thing that P points to should be changed to the value of 98. Now what happens if we do this? Look at the printed out here. I'm going to take away these two lines. Notice that this line is exactly the same as this line. This line we already know printed out 66. What's this one going to print? The exact same line. $98. Why? Will it be 98? Like 98 and 66 are the two running options. Why 98? Rationale. You assign that value at that address. So P, it has the address of C in it, and we're saying, hey, whatever is at that address, because we're dereferencing, whatever is at the address P points to, I want that to be 98. C is at the address P points to. So we're saying effectively, we want C to be 98. Let's find out. 98. So everybody think of this sorcery. We just changed the value of C without using the variable C. Uh, no, we could just do C equals 98. C is assigned 98. We could just do that. There'd be nothing wrong with that. And what you're kind of pointing out here is how utterly contrived this example is. Why do we go through all this trouble of getting a pointer to C, then changing what was at that address when we could have just said C equals 98 and been done with it, right? No, it's not really less overhead. This is merely a contrived example to help explain how pointers and dereferencing work. That's my only excuse for that. So, yes, normally you would just write that. The real power of pointers in this context comes into play when you use them as function arguments. And I can give a demo of that in a second. Because right now you're like, why would we ever do this? But I want to check in and see how people feel about this because it's a little bit voodoo. This is the part that is important to understand for the rest of it. That we managed to change the value in C without using C. We did it by looking at the address that was pointing to C. Once you have a pointer to that thing, you can change that thing. That's the takeaway right here. Let's write a function that looks like this. This is going to add 2 to the value that's passed in. Notice that I'm not returning anything. I'm going to ax this for now, but actually before I ax it, let me just throw it in here just in case anybody wants it. All right. Oh, we don't return anything. It's a void. All right. Let's do a little desk check run of this program. What's this going to print out? And you can also think of this from a JavaScript standpoint. This is going to behave exactly the same way JavaScript will at this point. Let's build it up, see what happens. 12. What happened to my stuff? Didn't I say add 2 to it? Why did it print 12 and not the expected 14? We didn't return anything. Definitely. If I pop over here, and I write something like this, this is the exact same function, right? And I say a equals 12, and I say add to a is still 12. The exact same thing happened in JavaScript has happened here. In JavaScript, we'd return it, right? We'd be like, okay, why don't we return the value a plus 2 instead? Let's say we don't want to return it. How else could we change this value? Sorry, could we change this value in x? How could we change that out here by calling this function? What would we have to change to make that happen? And I'll hint that, remember, we just changed the value that was in C without actually using C. Pointers seem like a good suggestion. What should we do? What should we do to make that work here? What's happening here is that we have a local variable a, and so a gets a copy of what was passed in, and then it modifies that copy. So a is 12 because that's what gets passed in, and so a is now 14, which makes sense because we just added 2 to it. But that's just a local variable. Back out here at main, we've got our variable x that never changed because a copy of it was put into a right here. A gets a copy of that. Yeah, let's try some stuff like this. So what if we made this a pointer to an integer? This is like a declaration right here. So we're saying a is a pointer to an integer. This line is going to have to be modified a little bit, though, because a is a pointer. It's like a gigantic number like we saw, and we don't want to add 2 to the gigantic number. We want to add 2 to the thing that it points at. We want to add 2 to the thing that's at that address. Close. What we want to do is we want to dereference it. So the other way, yeah. So dereference takes a pointer and turns that into the thing that it's pointing at. So this is saying, hey, whatever a is pointing at, I want to add 2 to it. Let's give this a build and see what happens. Warning, incompatible integer to pointer conversion, passing int to parameter of type int pointer. So telling us what to do. Take the address with ampersand. It's actually being that's a pretty heavy duty warning. So it's saying right here on our add to line, we're passing it an integer, which we are, x is an int, but it expects that for add to, we will get a pointer to an int. And so it's telling us to take the address with ampersand because address gives us the pointer to the thing. So we've got x, we've got a pointer to x right here. We pass that in to add to, and a copy of that pointer to x gets stored in a. So a is also a pointer to x at this point. And then on this line, we say, whatever a is pointing at, add 2 to it. Let's give that a run. There we go. So now we've written a function that changes one of the values back out here in the caller. So x is local to main, but by calling add to with the address of x, we managed to change the value in x. Where this becomes really powerful is if you have a function, again, this is kind of contrived, that needs to change a bunch of things. You can only return one thing in C. And so if we need to return multiple things in this here contrived example, here we've got a function that modifies multiple values. So that's often where you see it. A lot of functions return one thing, but also want to return something else. And so maybe they'll use the return value to return one value, but then they'll use a pointer type to return a different value as well, an additional value, I should say. They aren't really returned, right? I said returned, but I shouldn't have said that. You're totally right. There's really only one return value for a function. I like this question. Oh, this is a good one. I'm going to write another function. Void subtract 2. Uh, and I'll, oops, int a. And so the question is, let me re-simplify my code here. Get rid of this and this and this. Okay. So could we use like something like this? So use the ampersand inside this thing and do that. Oh, let's try it. I'll do a sub2 here. And this is just going to pass in x. And then we'll print it out again. So x was 12. When we add 2, it becomes 14. It should print 14. Subtract 2. Subtracting 2 should get it back to 12. But it doesn't. Oh dear. Why not? It has to do with how parameters work in C and in JavaScript for that matter. We call these being passed by value, these parameters. So what happens is when I say subtract 2 from x and x is 14, a is a different variable. It gets a copy of x. So it doesn't actually, it's not the same x. So it gets its own copy. And if we print out the pointer here, pointer in sub2, let's print out RP. And then I'm going to print out a pointer here in main. I'm going to print out the address of x, a pointer to x. So we can see what the address of x is. We can also see what the address of a is. And we see that they are different. So in sub2, the address is this number, oops, this number, and in main, the address is this number. So what that's telling me is that this variable a is in a different part of memory than this variable x, which makes sense because a is getting a copy of x. So they have to be in different parts of memory. So what we've done is we've gotten a pointer to a, but a is a copy of x. And then we've changed what that points at, but that just changes a, it doesn't change x. Does that make sense? Whenever you pass a thing to a function in C, it always makes a copy of that thing. Is memory for A temporary? It is. It only lasts as long as execution is happening within this function. A is local to this function. In fact, let me go off in the weeds for just a second here as an aside. If you had a function like this, whoa, here's a function that declares a local variable a. Could also be up here. This is bad to do because A's memory is good within the function, but then when you return a pointer to it, the caller can't do anything with this because A gets vaporized as soon as the function exits. So if you declare a local variable like this, it's bad to return a pointer to it because the variable will be gone. The pointer will point at garbage or nothing afterwards. Kind of garbage collection. It's not called garbage collection though. It's called, there's a name for it that I can't remember. No, there's a name for like automatically destroying variables when they fall out of scope. So it's garbage collection is more general. If you say garbage collection, it's like it, but garbage collection is able to handle things that are returned and or put another way, if we were doing this in the Go programming language and you did something like this is totally fine because Go will pay attention to who has a pointer to this thing and it'll keep this thing around as long as somebody has a pointer to it. A garbage collector is a type of memory manager that'll go through and be like, hey, I have this chunk of memory over here and nobody's referring to it anymore. So I'm going to get rid of it. And that's kind of a more complicated procedure than what's happening here, which is, oh, hey, I got to the end of the function, so I'm going to just deallocate everything that was declared in the function, period. Even if you return a pointer to it, it's gone. So it's kind of a garbage collection-y thing, but it's really simplistic compared to actual garbage collection. Let's see. What do I got? 10:45. Where do we want to go with this? Let's go ahead and throw this guy in here. I kind of don't want to leave without talking about how strings and pointers are connected. But I want to give you guys the opportunity to ask more questions here. We've got 15 more minutes. We do have tomorrow to talk more about pointers, but probably the more we talk about it today, the easier time you'll have with stuff today. So the other two things I wanted to talk about were strings and arrays, which are very related to this stuff. But before I do that, what's everybody thinking? Respond with an emoji. Rocket seems positive. Sure. Yeah, asterisk and ampersand. So ampersand is when you have a thing like an integer or a char, and you want a pointer to that thing. So here we have a thing, an integer x, and here we wanted a pointer to that thing. And I needed a pointer to that thing here because if you look at the function add to, it says, hey, I'm expecting an int pointer to an int. So address goes from a thing to a pointer, and ampersand goes from the thing to the pointer. Asterisk is the opposite. It goes from a pointer to a thing. So here we've said, give me a pointer to X. And here we've said, hey, whatever A is pointing at, add 2 to it. So use asterisk when you have a pointer and you want to get to the thing that it points to. And use ampersand when you have a thing and you want to get a pointer to that thing. They're opposites of one another. One turns it into a pointer, the other turns it back into the thing. Does that make sense? Or no? Thumbs up. Yeah, I'll run another example here with strings. I'm going to go back to char pointer land. That original thing. How do you run it? Like, how do you build the executable and run it? Is that the question mark? Or how do you run a shell? So the shell is just the bash shell, at least on Mac and Linux, and you can do the same thing in Windows. But oh, you know what? I totally dropped the ball on this thing, didn't I? Where is this? Did I not send this thing to you guys? Probably didn't send this to you guys. Something that would be really useful. This. So check that page out, Mark. Does that the quick skim of the top? Does that seem to does that answer that? I feel bad because I'm pretty sure I did not send that link out on Thursday. So I have to really seriously apologize for that. If there's stuff in here uh, that gets that you get stuck on, like the install of the compiler, like just reach out immediately. And like the challenge is that's just like an IT challenge to get the compiler working sometimes. So it's not one of the goals of this week is not get good at figuring out how to install a compiler. We should just be able to blast through that. So yeah, check that thing out. Oh my gosh, thanks for bringing that up. That should totally be in training kit. I need to get that link in there. Links in the project. Okay. At least it's somewhere. Oh man, that alleviates some of my guilt. Okay, let's look at this string thing really fast. In C, strings, constant strings are in double quotes, like this. And you notice something kind of curious here. We got a pointer to a char, a pointer to one char. All pointers just point to one address in memory, right? Like we've been talking. So if we're pointing to one address in memory, how do we have all these bytes out here? Each one of these characters is 1 byte long. So that's like, I don't know, 13, 14 bytes. How does this work? I'm gonna go ahead and print this out. I'm gonna use the %s format specifier to print a string. I'm gonna pass that string in there. Let's build that thing and run it. Hello world. So how did any of that work? I mean, this is just an address in memory. Let's print that out too. Sure enough, there's an address. Just one number. So what do you guys think is happening here? What does S actually point to? How could we figure out what was at that address? S is just one address, but when I tell it to print it out as a string, it prints the whole string. What if I want to print out the character that S is pointing to? What would I have to do here? What if I just want to print out that character? Let's start with the first character address and we'll be able to reference all the others. Well, let's print out the character that it points at. I'm going to print out %c to print out a single character and dereference S. Man, I wish I had another 20 minutes in this lecture. We would just slay with that. So let's print this out. Any guess what this is going to print? I'm saying print the character that is at the address S points to. Let's have a look. Capital H. All right. Well, we've only got one of those right there at the beginning. What do we want to do with this? What do we want to do with this? Let's have some fun. I'm going to take out our printf here. I'm going to write my own print string function. And it's going to take a char pointer. I'm going to call it P just to be different. And so let's print string S out. And we already saw we could print a character just like this. So let's comment all those out. Dereference P. All right. So I've changed some stuff around here, but really we're doing the same thing. I'm going to pass S into the print string function. It's here locally as P, pointer to a char. If I print it out, dereference P, we should be back where we were, printing out H, the first character in the string. All right. I'm going to show you guys a couple things right now that are a little bit weird. One of them is called pointer arithmetic. First of all, I'm going to start by saying these two lines are exactly the same. If you add 0 to a thing, it doesn't change it. So these are exactly the same line. But, VI, come on. This is interesting. If you add 1 to a pointer, it's going to point to the next address. So adding 0, it points to the same address as always. We saw that this printed out H. But this pointer arithmetic right here, this is kind of interesting. I'm saying take address P, go to the address right afterwards, Remember, an address is just an index into the big memory array. So this is like saying, oh, hey, if we were at index I, let's look at index I plus 1 and see what's there. So any guesses to what this is going to print, this line right here? We should probably get an E out of it because that's the next character in memory right after that thing. HE. P++ syntax, would that be appropriate here? Yes. Before I get there though, if I start writing code like this, what is this screaming for me to do? What should I be doing instead of writing code like this? Some kind of a loop would be nice, right? Let's see, how do I want to attack this? Because P++ is good syntax to use, and I do want to use it, but I'm not going to go there yet. Let's do a loop. How many characters in Hello World? 5, 6, 7, 12, 13. Is that right? Guess I'll find out in a second. Let's do one of these things right here, P plus I. Get rid of all this stuff. So I'll start at 0, so that'll just be P for the H. I will go to 1, and so on. I'm getting them all in different lines, which is kind of a bummer. Let's take out this new line, put them all in the same line, and then I'll put a new line at the very end. Hey, we've printed a string out. Although I had to know how long the string was. That's kind of annoying. When we printed it out with %s down here in this printf, we didn't have to tell it how long the string was, did we? Somehow printf knew when to stop printing. I mean, if we just kind of, how does it know when to end? Like, if I just put 99 out here, what's going to happen? Ugh. All kinds of garbage gets printed. How did printf know when to stop? How do we know when to stop? This was undefined behavior, by the way, because I was accessing elements past the end of the object. \0. What is \0? The null character. I'm going to shorten this a little bit. We'll get rid of 99. And I'll change this to something that's definitely too big, 30, still past the end of the string. I'm going to print out as decimal numbers now. Now, actually, let's print them out as hex numbers. Let's print them out as 2-digit hex numbers with leading zeros. There we go. This will probably look good for the first part and then turn into kind of garbage, but I'm going to run this again. All right, so I've printed out the first 30 characters of this string, which is clearly more than hello world. I printed it out in hexadecimal, and let's have a look at what's here. So I can recognize some of this stuff as ASCII. So 48 is H, 65 is E, 6C is L, L, O, 2C is comma, 20 is a space. Then we've got W, O, R, L, and D, and an exclamation point with the 21. And then we have a 0. We have a value of 0. And this is exactly what we're calling the null character here. This is how we know that the string ends. There are kind of two ways of doing strings in programming. One is have a bunch of characters in memory and also have a length stored somewhere, which is how languages like JavaScript do it, or languages like Python. Another way is to have what's called a sentinel value. that it's a value that has a special meaning that you can interpret in a special way. So if we have a string of characters, our sentinel value is 0, the null character. That lets us know that we're done with the string. So now I can just change the code to look something like this. In single quotes like this, a \0 means 0, the 0 character, as opposed to like a 0 integer. This is really common to see if you're dealing with chars, because this is in single quotes, it is a char. You could also write this if you wanted. But what we're looking for is that 0 value that we saw at the end of our string. So as long as the value that p is pointing at is not, p plus I, as long as the value that p plus I is not 0, let's keep on going. So let me change my code back to a C here. And I think that's it done. I know I'm over time here. There we go. So it stopped. So we just kept going until the value at address p plus I was 0. And as we saw here, that right here marks the end of our string. All right, I'm gonna call. 65 was A. Oh, yeah, so sorry, 65 decimal is A, but I'm printing these out in hexadecimal. That was a good catch. I was totally confused for a second. All right. I know I'm out of time. I wanted to show you 2 more ways of printing this loop, or printing the string in this loop. And so I'm going to add them here really quick and then paste them in for you. This first one that I'm going to show you is the mind blower. And here's why. Yeah, sadly, I'm one of the people that has to go because I have tons of stuff to do before a giant block of meetings this afternoon. But I did want to show you this punchline right here. These 2 lines are exactly equivalent in C. The specification goes so far as to say that they are equivalent in every conceivable way. This is array notation. This is pointer arithmetic notation. So we've already seen some pointer arithmetic up here. But what I'm saying is that these 2 lines, exactly the same. You can use them interchangeably. So I'm going to pop down here where I have every place I have dereference p sub plus I. I'm going to change that to p sub I. The difference between pointers and arrays in C is basically non-existent. It's one of syntactic sugar, and that's all. Pointers and arrays are the same thing. Arrays just give you a nice, easy syntax for doing pointer arithmetic, so you don't have all these parentheses and asterisks. So I wanted to point that out to you, no pun intended, so that at least when I'm programming in C, in my mind, when I'm thinking of arrays and pointers, they are the same thing, and it's just a matter of how I'm describing them in the code. If I have things that started off as pointers, I tend to use pointer arithmetic and not array notation. Yes, with so what Vim says, except with some caveats. Like when you declare a pointer, it doesn't necessarily declare memory for that. So this just declares enough space for a pointer, and that's all. But if you declare an array of 128 elements, this will declare space for 128 elements. So yes, pointers can be replaced with arrays, but there are some differences in how they get used when they're declared. But in terms of accessing them, this notation is equivalent. So this just gives us a pointer to nothing. This actually allocates some memory for us. And Q ends up being a pointer to the first element in that memory. So a little bit different, something to mess with. But I wanted to point out that equivalency. And you might also see this kind of notation occur in a function parameter list. This notation is equivalent to this notation, just in the function parameter list. I think that should still be good. Let me make sure I've done it right. See if we get another hello world here. Yeah. So this is the pointer arithmetic version, and this is the array notation version. These are the same, print string and print string 2. I'm going to do one more pointer arithmetic version using the P++ thing, which is a far more idiomatic in C. Probably see something like this. I'm going to go back to my character notation. We have no initializer here at the beginning of the for loop, which is why there's just a semicolon. We want to go while whatever P is pointing at is not equal to null. We'll print it out, and then we will add 1 to P. So this actually modifies the pointer itself. The pointer like starts off at H, and then it bounces to E, L, L, O, comma, and so on. So this is moving the pointer. Whereas in this version, P always stays the same, and we just do some temporary arithmetic here to add a value to it. This is more idiomatic in C. If you were reading K&R's C book, they'd shorten it to this even, because 0 is false. So if dereference P is 0, quit. But so that's print string 3. I'll post all these here in the channel. Make sure this works. Hello world. Alex, this question is so good. Does pointer remain modified after the loop? Yes. So check this out. Let's do print string 3. I'm going to print out the pointer. Well, I'm going to print out the pointer correctly. Here, I'll print it out before the loop and after the loop. And so if I run it, we see before the loop it starts here. After the loop, it's had some value added to it. It's gone from FAA to FB7 there at the end. So is that desirable? In this case, it doesn't really matter, because P is a local variable to print string, and it gets thrown away as soon as print string 3 is over, like all local variables. the variable p gets thrown away. This is actually why I really like this question. Uh, if we needed p down here again, like we needed it in its original unadulterated form, we'd have problems because we've munged it up here by adding a bunch of values to it. So if you needed p again down here in your code for some reason, then you'd probably make a copy of it and then use q down here. Mess up the copy all you want, but then you still have p remaining the same afterwards if you needed it that way. But in this function, I didn't really care. P gets munged, but then we're done with it. So the cool part about this question is that we're modifying this local p, but we're passing in this variable s. So this isn't necessary. This little bit I'm about to tell you isn't really necessary to grok it at this point in time, but just in case you are out there, variable s is a pointer to a char, which means s contains the address of a character. When you call print string 3, a copy of s gets put into p. So as of this line, both p and the s that's out in main, they both point to the same address out there. They both point to the H in hello world. But like I said, every single thing that you pass to a function in C, every single thing gets copied into that parameter. So here P becomes a copy of S. It's just like if you've been passing integers to a function, you get copies in the parameters. If you pass pointers, you get copies of the pointers. But a copy of the pointer is perfectly as good as the original pointer itself. They both point to the same address, and modifying the address is what you're after. All that'll come into play more if you have a pointer to a pointer. Ooh, that's where crazy stuff happens. But that's a story for another day. Let me give you guys this code. Any last minute questions? We're 15 minutes into lunch, and I have to blast out and get a burrito before I run out of time. The big takeaways for this is this arithmetic array, or this pointer array equivalence. And like I said, they're not exactly equivalent because arrays allocate memory for you, and making a pointer doesn't allocate memory for you. But when you're using them, that usage becomes the same. Oh, I'll post it. Yeah, I'll post it right after lecture here, Jameson. All right, I'm going to call this the official end of the lecture. I'm going to show you one more thing that you should never do, because this is one of my favorite fun toys. I'm going to keep this comment around. Let's see. So if you got to go, you got to go. This part isn't important. This is just good for a laugh. So I've said these things are equivalent. I'm going to declare an array here, initialize with 5 elements in it. And I'm going to also have a pointer. You can look into an array. I can say P equals A. P is assigned A. In this context, A becomes a pointer to the first element in the array. So P points to the first element in an array, that 5 right there. So if I print it out, we can just make sure that it prints out a 5. Should print out the first element. 5. All right. Let's do something a little bit fun. If I want to print out the second element, I can do this. Just like we saw before, right? So that prints out 7, which is element number 2 right there. We saw that this is equivalent, however, to doing this, right? So those should both print out 7. What's this going to do? What if I reverse the 2 and the P? That shouldn't matter, right? I mean, 2 plus 3 is the same as 3 plus 2. Sure enough, it doesn't matter. But I said these two things are equivalent. Never do this. This is just for a cheap laugh. What? 2 sub P? It still works. This is how much pointers and arrays are the same in C. Dereference P plus 2 is the same as P sub 2. Dereference 2 plus P is the same as 2 sub P. If nothing else, that should drive home how much array notation is just syntactic sugar in C. Again, never do this. All right, that was my fun little thing for the end of lunch. I really like this language, guys. I'm sure that you could tell because I'm just like, hey, it's sweet. It gets down pretty close to the metal, and when we talk about architecture later, you'll be able to see like how closely related to assembly, like machine instructions, the stuff that we're doing right now is. So enjoy. Keep those questions coming, especially if you have questions about install of compilers and getting the compiler to work. That link that I posted earlier, I'll post one more time. This document is a work in progress, so if you find stuff that worked for you that isn't in this document, please point it out to me and I'll add it to it. And let me know if you have any other questions. Have fun hacking today. And I'll catch you all in the afternoon. Or, well, I'll be around in the afternoon if you have questions. Have fun.